our GitHub repository for more details. And currently we are working on 2 new features and the Project Panthera. The first one is an analytical SQL engine for MapReduce. It's built on top of Hive. And the goal is to provide full analytical SQL support for OLI applications. And the second is a document store for better query processing on HBase. It is implemented as a co-processing application of HBase, providing document semantics, and more importantly, it's a significantly speed up query processing on HBase. Let's first look at the SQL engine. But in modern business application environment, SQL is still the most important query language to support. With 30 years of investment by the industry, with all of the existing users, legacy applications, third-party tools, all of them require full SQL support, or to be precise, full analytical SQL support for all applications. And in the Hadoop ecosystem, Hive is the system for data warehousing applications. Everyone loves Hive. It provided HiveQL, a SQL language with support a subset of SQL with its own extension. So, as I mentioned, all our customers actually love Hive. It significantly lowers the barrier to MapReduce. On the other hand, while there are continuous efforts in extending the SQL support in Hive, there are still large gaps with regard to full SQL support. Many important SQL constructs that are widely used in applications such as multiple select, complex subquery, and so on, are not directly supported in that today. And you may need to rewrite a lot of your existing queries, and there are some queries it's difficult to do, and maybe not able to do that. So we want to have a SQL engine, an analytical SQL engine for MapReduce. And this is this shows a high-level framework for any purpose engine. We start with a parser, which converts the query to the AST, the actual syntax tree. Then you have the semantic analyzer with various analysis and optimizations on the AST, and generate a execute plan to run on the underlying execution engine. And this is how our SQL engine looks like. We used an open source SQL parser, which converts SQL to SQL AST. Then we built our own SQL AST analyzer and translator, which performs a series of content-aware analysis and transformations, for instance, subquery nesting, multiple select support, and so on, and generate a Hive AST. Then we use the Hive semantics analyzer with the necessary enhancement that makes it possible instead or minus, so on, and which finally generates MapReduce jobs running on the underlying Hadoop framework. So this is how it works. In addition, there are many options on how this SQL engine and Hive can be integrated, or maybe keep them separate. But in any case, in our current prototype, we built a common driver which directed different queries to different classes of SQL and HiveQL. And then we use the Hive semantics analyzer as the common backend for both queries. So what's the current status of the SQL engine? We have built a prototype based on Hive 0.9, available as the GitHub repository. This is the early implementation that the proof point to showcase some advanced query part. For instance, some of the complex queries not supported actually can be run in the SQL engine, such as, for instance, subquery in where class, or in exist sum, and so on. So you basically can use subquery in your application. Second, correlated subquery. One subquery that refers to a table that is not in its from class. So for instance, in this example, the subquery refers to table T1, which is actually in its parent query. Scale subquery, a subquery only returns one value from random. So you can use it in any expression. For instance, you can use it in a select expression. And also popular subquery, the multi-table select, and so on. We also did some comparison between Hive 0.9 and the SQL Engine using the NIST SQL test suite. And widely used SQL Engine performance test suite. We published to run for both Hive and the SQL Engine. That in particular only run the select statements. And to verify the results, we also run those tests using a commercial relational database so that we can compare the results with whether Hive or SQL Engine is the correct result. So this is what we got. We collected over 1,000 queries from NIST. Among them, about 87 is related to the subquery and about 35 is related to multiple select. As you can see, the SQL Engine has slightly better overall pass rate. In particular, all of subqueries are multiple selected in NIST. None of them are actually supported by Hive 0.9, but most of them actually can run under the SQL Engine. So the test is we have a prototype and we showcase those advanced features of part. So what's the next steps to achieve the goal of providing full analytical SQL support for Hadoop and the Hive project? Actually, there are many different pieces contributing today. For instance, you need a parser, which is SQL compatible. You need to support multiple select, subquery support. You need to support the complete SQL data type system, and so on. So we have been using the merge era Hive 32 to track these different pieces. So pretty able to at those eras, and I think as a community we really figure out what's the best approach to address those gaps. So next is about the document store for better query processing on HBase. So first, query processing on HBase. With the container that you run the Hive or the SQL Engine of HBase, store your data, the Hive table in HBase, and then query the data, that data using Hive QL or SQL. With the container run a series of MapReduce jobs scanning those HBase tables. So why should I do that? This is because by storing the data in HBase for analysis, it allows several use cases which are not possible to just store data in HBase. For instance, streaming real data into HBase for analysis in real time, support high accuracy rate workloads so that you can keep your data output up to date. And maybe you want the same data in HBase for both analysis and for serving the online services. So a lot of people are actually doing that. However, there is actually very large overhead related to query processing on HBase. First, the space overhead, or storage overhead. HBase provides very flexible schema for accuracy schemas. So as a result, you need to store data physically as a multi-dimensional pair, where each cell is as a fully qualified key value pair. So each cell you need to store the low key, called family name, qualifier, timestamp, value, so on. And while on the other hand, the Hive table has a relational model which is a fixed schema. So this is how a Hive table can be mapped to a HBase table. As you can see, there are a lot of overhead in the HBase, and we did some simple example. In a simple example, we create an 18-column table and store the Hive table in HBase, and also optionally with the fast diff encoding HBase. This chart is simply compare the file size, the storage size. So HBase actually can be as bad as 3x. Space overhead can do as bad as 3x overhead. And the second property of the performance overhead, typically we see somewhere around the 4x performance difference running the query in HBase plus depending on the specific query. example, the full table scan is much worse. You can get 6x difference. There are many reasons for that. And one of the reasons is actually related to how HBase handles the data stress. HBase is provider support for high bit and current reload. Which actually means that whenever you read a column, you need to pay some small amount of overhead, for instance, and current control for your current reading. On the other hand, for analytical query, they are long-term read operations. So preferably you should avoid this type of current read overhead. So what we have done is we have implemented a document store on top of HBase, which greatly improve the current processing of HBase by leveraging both the reading model and the read mostly access pattern. So in the document store, a table, HBase table can be declared as a document oriented table of dots and the table creation time. So this figure here shows this data model. Each row in large contains a collection of documents in addition to the low key. And each document contains a collection of fields. So you can actually refer each field as a document and dot field. And physically, each document is mapped to a HBase column and is serialized using some serialization framework such as arrow, output, alpha, and so on. This is how a relational table, the Hive table, gets mapped to dots. So each column is actually in the relational table is mapped to a field in dot. So basically, multiple columns goes into a document, and the schema of the document is started just once, not for every node. So it can be reduced to start go ahead. In addition, each document is actually mapped to a HBase column, and the interface on each HBase column is unit to update. So the read overhead can now harmonize across different fields in the document. It is currently implemented as a HBase local process application and available at the GitHub project. So how do you build up? First, running query, Hive or SQL query on top. This is our primary use case. It's actually similar to running Hive on HBase today. You first need to create a class, the document table in HBase. We will talk about that in a while. Then you create an external Hive table with the data, just as you would do with any normal HBase tables. Create an external table using the HBase storage Panthera. Except that when specifying the HBase column mapping, the mapping between the Hive table schema to the HBase table schema, you use the document of field instead of the column qualifier. After you do that, the rest is actually transparent to all of the DML query that is selected. It's all transparent, and no changes are needed to query out to the storage handle. How to create a dot in HBase? To create a dot in HBase, the user actually needs to specify the schema and the serialization framework for each document. So in this case, you first specify this table is going to be a dot table. And then you will specify what the document contains and the schema for each document. So this information is automatically saved implemented by the code professor. This actually means the user, the schema of the table is actually fixed and predetermined as the table creation time. It is okay for the Hive SQL query to have a fixed schema anyway. So how do you rewrite that? Well, again, it's transparent to the user. You can continue to use the scan, get, scan, put, delete, and also those filters. Except that you just need to specify document or field instead of column qualifier. So in this case, you basically specify D1.F1, D1.F1, and so on. And the mapping between the document field, the qualifier, is automatically handled by the code processor. Currently, in the document implementation, there is one extra constraint on the put and delete. That is, currently each document is mapped to a column, a column. And in HBase, the column is the unit to update. So when you want to update some field, delete some field, the system will check whether all the fields in the document is specified. And if not, we'll give a warning for push, checking those missing fields now. And if you want to throw an error for these, this is what we do today. But this is again only for the Hive query because only insert one complete node. So let's actually come to results. So we created a very simple method now. A 18-column table, a Hive table, stored in HBase, and we load over 500 million rows into the table. So this is a comparison of the table storage size with different objects stored in the normal HBase table using fast encoder, using DOS with the fast encoder. Because the DOS has a mapping, the document column is actually orthogonal to all of the encoding scheme. So you can see, depending on how you compare, basically build up to 3x storage reduction with DOS. And the second is the data loading part. So you can load the data into the system in two ways. Either through a bulk load in HBase, or you will just use a Hive insert statement, insert into. So this again, this compares the different scenarios. So for overload, using the DOS is build up to 2x speedup, and using Hive insert, we build about 3 to 4x speedup for insert. And then the select performance. Essentially, this is a simple query. It's essentially doing what is we select the various number of columns from the table. And this one compares different scenarios with using different number of columns. So essentially, with DOS, using our whether you use the fast or not, it gives better performance across the board. And when the number of columns, when the number of columns to read increase, the performance benefits actually also increase. So up to 2x speed up when you read the 18 columns to its full extent. But it still gives great performance. I think it's about something like 30 to 50x different, even if you just read one column. Okay, in summary, well, Project Panthera is our focus of efforts to enable better analytics to create an analytic base. And currently we're working on both the SQL Engine and the document stocks. So please take a look at those GitHub repository as well as those research areas. Okay, this is all I have today. So this slide and all the other information actually available at our website, our blog site in software.meetup.com. By the way, our team is based in Shanghai, so welcome to Shanghai if you want to sell in Shanghai somehow. Thank you.
So for the first part of the talk, you support SQL and you do. So do you support correlated subqueries and how do they perform? Correlated subqueries.
Correlated subqueries.
Yeah.
So what's
Are they supported and what is the performance?
It is supported, but we have not done any serious performance measurement yet. But it's supported.
So the performance for the HBase, did you compare it to the relational?
No, we do not compare with the relational, and I mean, typically we compare using variety data to utilize the relational database. At least not the one we can afford.
Question for Jason?
So
which one did you look at? This is part one. And part two, in terms of why HBase, in terms of Panthera, if I remember correctly, HBase is not consistency. Right? Consistency and availability. It's not the right use. So why I was interested in our use, the use case is primary analytics, which is mostly read. So consistency is not a concern for, this is not a major concern for the analytics. Well, HBase is very, it is durable. So what's the first step? Okay, we have now to talk about, there is a TPCH part in Hive, which I think will be taught by Facebook, and we actually have run a Hive, but we are currently looking at whether we can run an unported version of TPCH on this SQL Engine. We have not done it yet, so we will look at that.
How do you retrieve data from BOD? So is that controller format, right? The data in the BOD. Is that in the controller format? Yeah. How is data stored there?
It's stored the arrow. It's still doing the arrow.
Okay, so then how do you take out the data?
Well, I mean,
comparing HBase and with the.
Well, you mean the user or our implementation? The user just deal with
the user.
The user is, can see this very example. Or the user will read the data. It's actually same as you would do basically it's actually exactly the same as you would do to read the column in HBase, except that instead of if you have instead of using a column qualifier, you use the document.field to record the data.
Okay, for each. Okay.
Yeah.
So you just specify that.
You can do that in scan, you can input, delete, and view.
Okay. Thank you.
So in your HBase implementation, what are you using for secondary indexes?
We are not using anything for secondary indexes.
Thank you, Jason.